Something is wrong with the oldest light in the universe. Not wrong in a way that's easy to dismiss. Not wrong in a way that a footnote can fix. Wrong in a way that has kept astrophysicists quietly rewriting equations they spent their careers believing were finished. In July 2022, the James Webb Space Telescope sent back its first deep field image. The world held its breath. What came back was extraordinary. Not because of the beauty, though the beauty was staggering, but because of what was hiding inside that image that nobody expected to find. Galaxies. Old ones. Impossibly old ones. Not old the way a redwood is old. Old the way a contradiction is old. The kind that doesn't get smaller when you examine it more carefully, but larger. The standard model of cosmology, the framework describing how the universe evolved from a single hot, dense point into everything we can see, makes very specific predictions about how early galaxies formed. It says they build slowly. They begin as small gravitational knots of gas and dark matter, gradually merging over hundreds of millions of years, slowly accumulating mass, slowly kindling stars, slowly becoming the luminous structures we now map across the sky. That picture took decades to construct. It was tested by every telescope we had. It held. James Webb shook it in the first week. What researchers found inside those early images were galaxies that appeared ancient, structurally developed, massive far beyond what the timeline of the universe should have permitted. And they weren't rare outliers at the edge of detection. They were distributed throughout the field. Multiple independent research teams looked at the same data and arrived at the same uncomfortable conclusion. These galaxies had no business being there. One team led by astronomer Evo Lab identified 6 candidate galaxies in a relatively small patch of sky. When they calculated the stellar mass of these objects, the total weight of all the stars inside them, the numbers didn't reconcile with anything. Some appeared to contain as many stars as the Milky Way. Our galaxy took roughly 10 billion years to assemble. These objects existed when the universe was less than a billion years old. Some of them existed far earlier. To understand why that is a genuine crisis and not just an inconvenient footnote, you have to hold the scale of cosmic time in your mind for a moment. The Big Bang happened approximately 13.8 billion years ago. The universe has had nearly 14 billion years to produce everything we can observe. Every galaxy, every star, every atom of oxygen and carbon and iron that makes up your body and the ground beneath you. That is the full budget. The complete allowance. Now take away almost all of it. These galaxies existed when the universe was around 500 million years old. Some of the objects Webb has since confirmed existed even earlier than that. One galaxy, catalogued as JADES, GS, Z14-0, has been spectroscopically confirmed to have formed just 290 million years after the Big Bang. 290 million years. That sounds long until you realize it is roughly 2% of the universe's total age. It would be like finding a fully grown ancient oak, with dense bark and deep roots, standing in a forest that was supposedly seeded last Tuesday. But here is where it becomes genuinely strange. Inside that same galaxy, JADES, GS, Z14-0, astronomers detected oxygen. That detail sounds minor. It is not minor at all. Oxygen is not a primordial element. It was not produced in the Big Bang. Hydrogen was there, helium was there, trace amounts of lithium. That is the entire original inventory. Oxygen is forged inside stars, in the nuclear cores where temperatures reach tens of millions of degrees, and it only escapes into space when those stars die. In catastrophic explosions, in the slow, luminous exhalations of stars far larger than our sun. For oxygen to be detectable in a galaxy that early, entire generations of stars had to have already lived complete lives and died, long before the galaxy we observed had even reached the age we caught it at. Multiple stellar generations. In a universe that was barely born. The timeline, under everything we built to understand the cosmos, simply does not work. Researchers immediately asked the obvious question. What if the measurements are wrong? It is the correct instinct. Science demands skepticism before it permits revision. And for a time, there was genuine hope the answer would be something routine. that instruments were misreading brightness, that distance estimates were being inflated by some systematic error, that the most extreme candidates would quietly dissolve under more careful scrutiny. Then the spectroscopic confirmations started coming in. Spectroscopy is the gold standard in observational astronomy. Photometric measurements estimate a galaxy's redshift, and therefore its distance, from the color of light passing through a set of filters. It is useful. It is also approximate. Spectroscopy reads the actual chemical fingerprint of the light itself, the precise wavelengths of absorption and emission lines that correspond to specific elements and specific velocities. It is far more precise, far harder to mislead. One by one, the most extreme candidates held up under spectroscopic analysis. The galaxies were real. The distances were confirmed. And the mass problem, in several cases, did not shrink. It deepened. So if the measurements are right, something in the model has to give. And researchers began reaching for whatever could explain what they were seeing. The most conservative attempt involved star formation efficiency. Under standard cosmological models, when enormous clouds of gas collapse under gravity to form stars, the process is turbulent and inefficient. Radiation pressure, tangled magnetic fields, the violent outflows from newly born massive stars, all of these disrupt the collapse. In a typical star-forming region, somewhere between 10 and 20% of available gas actually ends up locked into stars. The rest gets blown away or dispersed before it can collapse. For these early galaxies to have accumulated so much stellar mass so quickly, they would need to have converted nearly all of their gas into stars. Efficiencies approaching 100%. That doesn't just strain the model, it invalidates the physical mechanisms we believe govern the process itself. Gas does not behave that way. At least, it is not supposed to. Some researchers proposed that the very first stars were fundamentally different from the ones that exist today. More massive, shorter-lived, more efficient in the way they processed gas and returned heavy elements to their surroundings. That the distribution of stellar masses, what cosmologists call the initial mass function, simply wasn't the same in the universe's first few 100 million years as it is in the universe we now observe. That is possible. It is also, at this stage, less an explanation than a label. A technical name we give to something we do not yet understand. Others went further. James Webb also discovered something it wasn't specifically sent to find. Scattered across its deep field images is an entire population of compact, intensely bright early objects that researchers have started calling little red dots. Dense. Luminous. Strange in ways that don't fit cleanly into existing categories. Many appear to be powered not primarily by starlight, but by actively accreting supermassive black holes, quasars, or what astronomers call active galactic nuclei, energy sources so violent they can outshine the combined output of hundreds of billions of stars. If some of the extreme mass estimates were contaminated by quasar light rather than stellar light, the galaxies would be less massive than calculated. The problem would shrink. For some objects, this explanation genuinely applies. But not for all of them. Spectroscopic analysis of the most carefully studied candidates shows the core tension persisting even after accounting for AGN contamination. The most challenging galaxies remain challenging. And then there are the researchers not adjusting parameters. They are asking whether the foundation needs to change. The framework underlying modern cosmology is called lambda CDM. Lambda for the cosmological constant, the term representing dark energy, the force driving the accelerating expansion of the universe. CDM for cold dark matter, the invisible mass that shapes how structures form. It is among the most precisely tested theories in the history of science. It predicted the large-scale structure of the cosmos, the way galaxies cluster across hundreds of millions of light-years, the faint thermal echo of the Big Bang that still permeates all of space. Generation after generation of observations confirmed it. And yet, astronomer Mike Boylan-Colchin published a careful statistical analysis of the most extreme Webb candidates and reached a conclusion that was measured in tone but significant in implication. These galaxies, if they are as massive as they appear, are not merely unusual. They are not the tail of a statistical distribution that might occasionally produce an outlier. They are implausible at a level that crosses from anomaly into genuine tension with the model. A tension that cannot be easily absorbed into the existing framework without changing something important about it. Not proof that lambda CDM is wrong. A stress fracture. A place where the model bends under weight it was not designed to carry. This tension is not entirely new. Earlier telescope programs had already hinted that the universe's large-scale structure might be slightly more concentrated than lambda CDM predicts, a discrepancy known as the sigma-8 tension. James Webb did not invent the problem. It walked into an already complicated room and turned up the lights. What makes this moment genuinely unusual in the history of science is not the existence of anomalies. Every generation of scientists has had to live with anomalies. What is unusual here is the pattern. The consistency across methods, instruments, and research teams. The fact that independent scientists at independent institutions, using independent analyses, keep arriving in the same uncomfortable neighborhood. Multiple massive galaxies confirmed too early. Oxygen present where it cannot yet have formed under any standard sequence. Star formation efficiencies that defy known physical constraints. Compact luminous objects that don't map cleanly onto any established category. A statistical pressure on the model that grows rather than fades with better data. This is not noise. It may not yet be a revolution, but it is something real, and something growing. Here is what the data keeps nudging toward, even when researchers are careful not to say it too directly. Either the early universe found ways to build structures faster than we thought possible through mechanisms we haven't identified yet, or our understanding of what happened in the universe's first few 100 million years is missing something fundamental. Not collapsed. Not wrong in every detail. But incomplete in a way that matters. In a way that will require, at minimum, revised physics, or a revised history, or both. This is familiar, even when it feels unprecedented. Every generation of scientists has reached a point where the major framework seemed mostly complete. Where the remaining work was understood to be filling in details, confirming predictions, closing open decimal places. And then something turned up that didn't fit. Not a small something. A structural something. The photoelectric effect didn't fit classical electromagnetism. The perihelion of Mercury didn't fit Newtonian gravity. The accelerating expansion of the universe didn't fit any cosmological model that existed before 1998. Each time, the answer wasn't that the previous science was useless. It was that the previous science was incomplete in a specific way, and the incompleteness pointed, if you were willing to follow it, toward something deeper and more accurate. James Webb is pointing at something. The telescope itself is worth holding in your mind for a moment. It orbits a gravitationally stable region of space called L2, sitting roughly 1.5 million kilometers from Earth on the side facing away from the Sun, bathed in permanent cold shadow. Its primary mirror spans 6.5 meters, 18 gold-coated hexagonal segments of beryllium, assembled into a surface precise enough to function as a single instrument from 1 million kilometers away. It sees in infrared, in wavelengths invisible to human eyes, the same wavelengths that carry the light of the earliest galaxies, light stretched by the expansion of the universe across 10 billion years of travel until it no longer resembles the high-energy radiation it once was. It was designed to look back to the first stars, to answer questions we had spent decades formulating precisely, to see the universe's childhood and tell us whether the story we had constructed was correct. It looked. And in the looking, it created questions we hadn't had the instruments to ask before. That is how discovery actually works, most of the time. Not as a clean march from confusion toward certainty. More like a hand reaching into darkness, finding the edge of something enormous, and slowly, carefully, trying to trace its shape without knowing in advance how large it is. We have been watching the sky for thousands of years. We decoded the mechanics of the planets, mapped the distances between stars, discovered that the universe is expanding, detected the afterglow of its birth. With each layer of understanding, we did not find closure. We found depth. Not a ceiling, but new floors beneath the ones we had already reached. The galaxies that shouldn't exist are not a failure of astronomy. They are its highest possible expression, the moment when a tool we built becomes precise enough to find the thing we hadn't anticipated. The seam in the story we thought we knew. The question inside the answer. Nobody has a good answer yet. That sentence sounds like a problem. It is actually the most alive place in all of science right now. Because somewhere in the data James Webb is still transmitting back to Earth, in the spectra of ancient light, in the chemical signatures of oxygen present before it should have been possible, in the quiet, persistent mass of galaxies that should not yet exist, somewhere in all of it, a new answer is forming. An answer that will change. In some way none of us can yet fully predict what we believe about the beginning of everything. The universe did not ask for our permission to be strange. It never has. And if the history of discovery means anything at all, the strangeness is exactly where the truth has always been hiding.